Yes. Okay, great. So our final speaker for this afternoon is Adam Levine from Duke, and he's going to tell us about Khovanov homology and cobordisms between split plates.
Well, thank you, everyone. It's really great. This conference has been fantastic. I'm sorry not to be there in person, but I really have been watching most of the talks from my office and from home, and it's just been just a great conference. I very much miss being there in person. The Topology conference was among the first conferences I went to. I think back in 07 or 08 was my first time, and the big one in 09. And those were really just like really great, memorable weeks. And I hope we'll be able to come in person again sometime soon. So, and also I just want to say that, like, looking around the room here, it's really nice seeing a lot of, familiar faces, but also an awful lot of unfamiliar faces. And I feel like during the past couple of years, I've just been seeing so many, like, especially graduate students and postdocs who I haven't really gotten a chance to meet, except maybe through very quick Zoom interactions. But it is just very exciting to see so many young folks just like starting out in this field and doing really great work. It's wonderful. Okay, so I'm going to talk about a project. This paper came out towards the beginning of the pandemic, but time has no meaning anymore. So this and all of this is joint work with Onkar Gujral, who was an undergraduate at Duke, who wrote a senior thesis with me. He's now at MIT in graduate school and really doing a great job. So, okay, so the basic question, we've been talking, of course, a lot about Khovanov homology this week, is to what extent can Khovanov homology detect the linking of disjoint surfaces in pore space? And everything we say is going to be in the smooth category. We're going to be talking about smoothly embedded surfaces, generally in ordinary, R4 or S3 cross an interval. Okay, so what does Khovanov homology even have to do with surfaces in pore spaces? So we've, by this point, I think for any link, we have this bigraded abelian group called Khovanov homology. And a link cobordism, the basic object of study here is going to be link cobordisms. A cobordism is going to be a compact-oriented, smoothly embedded surface in the product of a three-sphere with an interval interpolating between two links. And we'll call C a concordance if every component of C is an annulus that goes from one component to a component of L0 to a component of L1. So in particular, they have to have the same number of components. Of course, the classification of knots up to concordance or links up to concordance is a very interesting question, and a lot has been said about that already. What happens is the way that these work with Khovanov homology is, and we've alluded to this, of course, as we've been going along, is that whenever you have a link cobordism between two links from L0 and L1, you get an induced map on Khovanov homology. So Khovanov homology, really, you get a chain complex, and you get a chain map between those chain complexes induced by this cobordism. Now, it's homogeneous with respect to the bigrading. It's degree 0 with respect to the homological grading, and the degree with respect to the quantum grading is determined by the Euler characteristic of the cobordism. And this is functorial under stacking. So if you take two cobordisms and you stack them end to end, then you get then the induced maps compose. And of course that last bit is sort of basically just a consequence of the definitions. The way you set these up is that you break the cobordism down into little elementary bits. You can think about it as a sequence of Reidemeister moves. You're watching your links move around in space, and so you have Reidemeister moves, but then you have moments of births, a little circle being born, or deaths, a little circle disappearing, or a saddle move that does this. I'm sorry, I don't have slides of all of that. Okay, now it's a theorem that these induced maps are an invariant of the surface, and they're an invariant of the surface up to isotopy. Now, maybe I'll spell this out. So what is that? What do I mean? It's a theorem of Carter or Saito, maybe. I'm not entirely sure the intellectual history here. That two of those movies represent isotopic surfaces if and only if they can be broken down, if and only if they can be related by some sequence of moves. So, for instance, creating the heights of sort of distant parts of the surface, but also what they call the movie moves. And there are 17 of them. And it's a theorem that these maps induced on Khovanov homology are unchanged under movie moves. And so thus they're really representing a topological invariant, smooth invariant of the surfaces themselves. And I'll get just to mention a little bit of the history there. Khovanov and Jacobson and Barnatan each sort of gave independent proofs of this. This is, gosh, about 2004 or so, 3 or 4 that these results came out. And those original results were only actually proving an invariance up to an overall sign. And then there have been various ways of fixing the sign ambiguities due to Carmen-Catrao, and then simultaneously, roughly, Clark, Morrison, and Walker. And then recently, within the past year or two, there was a paper by Sano, which sort of did this in a different way. I'm going to sweep all of that under the rug. So everything I'm going to say is going to be up to sign. Presumably, you can build the same fixes into the work that Onkar and I were doing. But yes, so that's the one little caveat about the invariance results. Oh, and I guess I should say, originally these things were proved for isotopies in R3 cross an interval, not S3 cross an interval. Okay, now you might be wondering what's the difference there. Surfaces could be the image of an isotopy is tracing out a 3-dimensional thing in 4-dimensional space, and the pointed infinity cross an interval is a 1-dimensional thing. So conceivably, an isotopy could cross that, and you might have to do. There's a little bit that you have to worry about, but actually, thanks to work of Morrison, Walker, and Vedrick a couple years ago, the isotopy statement holds at the level of S3 cross an interval. I should say that also there's this notion of dots on cobordisms. You can put a dot on a surface, and that changes the that may change the cobordism, the induced map. Okay, great. So here's the theorem that we're going to discuss. When I say that we're interested in how does Khovanov homology see linking between surfaces, right? Just like we could talk about links of curves in 3 space, we could talk about links of surfaces in 4 space. Okay, and we could either talk about closed surfaces, that's hard, or we could try to talk about surfaces real boundary, that's what we're going to do. But how do we try to measure that? Notice that there's no notion of the linking number. The dimension is wrong to try to get a linking number between those kinds of surfaces. But here's what we can do. Let's suppose you have 2 links, and what we're going to assume, as in the title of the talk, is that these are each split links. Okay, so L0 is a link, and it's decomposed into some collection of sublinks, L0 through L01 through L0K. I will always be using superscripts to indicate that sort of what part of the link I'm talking about. And I'm going to assume that these components of the link are all contained in disjoint 3 balls. Okay. I'm going to allow, so sometimes we use the word split link to mean that it's like literally split into a bunch of knots. We're going to allow ourselves to work more generally. The individual parts could themselves be linked, could be links. The individual parts could also be empty. That might be useful to us sometimes. Okay, so supposing I have 2 links of this form, and let's assume that we've actually, after isotoping things sufficiently, we have the same sort of decomposition into 3 balls. Okay, they're all like living in the same regions of 3 space. Okay, I'm going to call a cobordism from L0 to L1 partition preserving if the surface breaks into a bunch of disjoint surfaces. Okay, namely there are k separate surfaces, and each one of them is itself a cobordism from the jth part of L0 to the jth part of L1. And here's the picture that we want to envision. I have these 2 surfaces. Okay, so I'm just sort of respecting the breakdown of the surface of the link into its pieces. Now, I'm not necessarily saying that I have a surface that is actually split apart. right? It's either the surfaces don't necessarily have to live in like cerebral approximate identity. We'll get there in a second. Great. Okay, so now we're going to define, we needed a term for this. We're going to say that two such cobordisms, these partition-preserving cobordisms, are partition homotopic if individually the jth part of one of them is isotopic to the jth part of the other one, rel boundary, those boundaries fixed for each j. So that is to say, like, the first part of one is the same as the first part of the other. Second part of the one is the same part of the second part of the other, but it's not necessarily that they're the same length, right? So that the isotopy from Cj to D, C1 to D1 might pass through C2 or D2 or something, right? They might collide in the course of those things, but this is it's a sort of, it's like thinking about link homotopy. Okay. No, sorry, it's the opposite of thinking about link homotopy. All right, now, what you can see in a fairly straightforward way is that any partition-preserving cobordism is partition homotopic to a split cobordism. You basically just kind of bring the jth part, you think about, just ignore the other components, right, of the link, and you just kind of squeeze that part down until it lies in a ball, and maybe collides with the other things. But here's the scheme that I want you to imagine. I'm just gonna yank everything apart. Okay, and of course the links at the beginning and the end were already split links, so I haven't really changed anything on the well, I guess even if the if I want to do this rel boundary, the links at the beginning and the end were already split links, so I have to I'm only doing these changes sort of in the interior. Okay, that's the mental picture you want to have of this operation. Okay, now that I've said all of that, here's a theorem from well, I was working on, I worked it out today as I believe March 811th, 2020. So it's a theorem that we proved earlier this month. This is so here's the claim. Supposing I have these two split links, suppose I have two partition preserving cobordisms between them, and that these are partition homotopic. And the theorem is going to tell us that the induced maps are the same, and they're the same up to an overall sign. And if you were to really try to work at it, I'm sure you could get rid of that sign dependence. But for the purpose that we were sort of originally interested in, equal up to an overall sign is good enough, as is often the case in these discussions. Okay, any questions about what the theorem is saying?
So I could interpret it as kind of a negative result, that it's not going to distinguish things.
That's exactly right. It's not seeing the linking between the cobordisms at all, right? It can't.
So we can restrict just to totally partitioned cobordisms.
That's right. That's right. So let me give you one instance of this. Oh, actually, before I say that, what can we say about these totally partitioned cobordisms? Well, there's a Kunith theorem for split unions of links. Okay, so Kunith theorems are a lot easier to state if you're just working over a field, so you don't have to worry about all of those like Tor or X terms or whatever. So let's just say this over a field. If you take a split link, then the Khovanov homology of a split union of the components is just the tensor product of the Khovanov homologies of the pieces. Okay, and over Z you have to throw in some Tor terms, but that's fine. You could say this, make this as a statement of someone said in the talk, I don't, we really shouldn't think about Khovanov homology as a group. We should think about it as a chain complex up to homotopy equivalence in some sense, and that means that's maybe a better way to say this. Okay, great. Now, if you have a split cobordism between split links, okay, then the assertion is that, so that is when you have the split cobordism, so it's living inside of the these just little cylinders, then the map on Khovanov homology is also a tensor product. Okay, it's a tensor product of maps. Okay, exactly in this fashion. And now what our theorem says is that this is true for any partition preserving cobordism, right? It's just going to necessarily be this tensor product. Okay, which is maybe surprising, right? Now you might have thought that, like, you know, the linking would sort of convolute this map in some way, and so it's not. But the claim is that it does. Okay, let's give a consequence of this. So as I said, you could take some of those pieces, the L0Js, to be empty if you like. Okay. Now a cobordism from an empty thing to an empty thing is just a closed surface. Okay. So the reason that we were actually interested in this question, I'll tell you the reason behind that, momentarily, is the following. You could imagine you have a cobordism from some length from L0 to L1. Okay, and you could imagine taking some closed surface in the complement of in the complement of L0, the complement of the cobordism. Okay, and you could ask, like, does the presence of that surface change the cobordism in an interesting way? Okay, now if it's something other than a torus, then it's changed the Euler characteristic, and if it changes the Euler characteristic, then of course you've screwed up the gradient shift. So it might change it, but of course, like, does it actually change it? And is the change the same or different than, like, if you had the surface being sort of removed, like in a little ball, a little 3-ball, or 4-ball sort of disjoint from the surface, right? That would be on length versus length. Okay, and the assertion is that it does not see that linking at all. Okay, so that is to say that the Khovanov homology induced by this union of the original cobordism and this little closed surface, if you add a torus, you multiply by 2. If you add a dotted sphere, then you preserve the map, you multiply by 1. And otherwise, adding a closed component kills everything. It completely kills the maps. Okay, and you should think about this as being basically a lift of the 3-dimensional relations. And this was known. To hold if your surface was, like, on length. Right. So the statement is that the Khovanov homology also can't really see the knotting of closed surfaces in any reasonable way. That's a result of Tanaka and Rasmussen. And this is what we can deduce. Okay. Special case of this is closed surfaces, as I was just alluding to, right? If you were to think about a closed surface in four space as being a cobordism from the empty set to the empty set, the empty link, the Khovanov homology of that is Z. So the map, the induced map, is just a number, okay, which was called the Khovanov-Jacobson number. And in the early days, it was hoped that maybe that Khovanov-Jacobson number would be like an interesting invariance of knotted surfaces and could distinguish it. But pretty early on, it was observed, as I said, by Tanaka. Oh, yeah, so for a connected surface, it really only depends on the genus. For the connected surface, the Khovanov-Jacobson of a torus is 2, and of a surface of any other genus is 0, or a dotted sphere gives you 1. Okay, and then that's exactly the same here for surface links. Okay, the Khovanov-Jacobson of a surface link, you could pull the components apart and then you just multiply the numbers. Okay, so yeah, I guess this isn't sometimes disappointing, right? Like the Khovanov homology is not seeing the 4-dimensional linking. You might think. You might have hopes that it would. I don't know if this is a good result or a bad result.
Is this corollary in K bigger than 1? Like, I mean, or even when there's 1 component, is it just
for K equals 1? This was known. For K equals 1, this was known, and then it's our result. But let's say that when you have a link of surfaces, well, you could just pull the components apart and then multiply the known result.
But I'm just saying that the fact that it depends upon the genus is not as strong as the fact that it's plus or minus 2 if it's a torus and 0 otherwise. You're saying that's what was known as well. Right. So yes, okay. So I should have said is that it depends only on the genus, which is to say that it's 2 for a torus and 0 for anything else. That makes sense. So. Okay, now I'll just mention, and I'll come back to this at the end. I feel like the ribbon concordance had this great moment in the sun, and in fact there was a
in Quanta Magazine, which is the magazine that's published by the Simons Foundation, there was just a story about this. I'll allude this. I'll say more about that in a little bit. But the reason that Onkar and I were studying this question is that it was to generalize some work that I did with Ian Zemke, based on the big work that Ian did about homology, which is to say that a strongly homotopy-ribbon concordance induces an injection on Khovanov homology. And I'll define all of those words later, but I will say, like, in some sense, we wanted to be able to use, we had an application in which we really needed this corollary here. We really wanted to be able to pull off closed components and say that the closed components didn't affect certain maps. Initially, we wanted to just be able to pull off closed spheres, but then we realized, like, we can actually pull off closed components that, you know, of any genus. So that was why we were doing this, and I'll come back to that later. But this is because this is really a sort of a quantum topology kind of talk. I'll go into some more detail about sort of how the proof of this works than I have in other settings in which I've discussed this, which is a nice opportunity. There are plenty of other places where you can hear more about the ribbon concordance applications. Okay, great. So what I want to talk about really is a great result that's called the Batson seed deformation of Khovanov homology. And this was alluded to in Gage's talk the other day. And I think it's very valuable. And I hope, as I was listening to some of the other talks here, I was starting to think about whether any of the of what I'm going to tell you about maybe has any applicability in other settings as well when starting to think about tangles. So this is a result of Batson from about 10 years ago. So here's what we're going to do. We're going to start by thinking about sort of standard, good old-fashioned classical Khovanov homology, right? It's and so we're going to let CKH is going to denote the Khovanov complex. If you've never seen it before, I would encourage you to read Barnaton's papers, or Khovanov's papers if you're brave. But okay, so I'm going to assume that we have some familiarity with that complex. I'll draw an illustration of it in a moment. And we're going to take coefficients in an arbitrary commutative ring R within it. But of course that just means taking the tensor product with that ring. Okay, and a weighting on this link is going to be a choice of elements of the ring associated to each component of the link. Okay, so that's a very general notion. We could make them all 0 if we wanted to, but we could also make them, you know, some interesting choices. Okay, you can even just do this with Z and maybe weight some of the components with some numbers and others with other numbers. Okay, great. Now, what Batson and Seed showed how to do is that given a weighted link, they're going to give a way of perturbing the differential. The Batson-Seed differential, dBs, is going to be the Khovanov differential plus another term phi. Okay, and phi is going to have a shift with respect to the gratings. Okay, it's not, so this new differential is no longer going to be homogeneous with respect to the whole bi-grading. There's a single grading on the theory that will work. But this is going to become some kind of filtered complex, right? And anytime you take a differential on a chain complex and then you perturb it by adding some little phi like that, you can turn that into a filtered complex. Okay, so here's let's just show an illustration. So here's going to be my link. Link is the Hopf link. You break it down into these 4 different resolutions, and then associated to each of the resolutions, you take a tensor product of states, or a tensor product of some 2-dimensional vector space, a 2-dimensional free module over R, and then you write down the differential in some way. Okay, and hopefully people have seen some version of this picture before. Okay, so let's just observe that for each sort of time when I'm changing the resolution of one crossing. So here on these 2 sides, I'm changing the lower crossing. I get an induced map. Okay. I haven't seen this before. I'm sure this conference has been a blast. Okay. So now here's going to be the weighting idea, and I'm just going to say this in sort of generality. R is like any ring, and A and B are any elements of the ring associated to the two components B. So there's B on this component, A on the other one. Okay. Now, what are we going to do? DKH is still going to be the same. B is going to be the what arrows that I've indicated here in red. Okay. And what are they? Well, they are associated to every crossing. I'm basically just going to throw in the reverse map. So if I think about the map that goes from here to here, can everyone see my mouse as it moves around? I hope. So think about the map that goes from here to here, right? I'm thinking about that as a merge between two components. Going in reverse, I can think about that as a split. Okay, now a split induces a map from 1 to 1 times x plus x times 1 and x to x times x. Okay, and that's the map. So I'm just going to basically throw in that extra differential, but I'm going to throw it in with a little bit of a weight added to it. And what's the weight that I'm going to add? It's going to be the difference of the two weights between the overcrossing and the undercrossing. Okay, now there's some rule. It's supposed to be like the overcrossing minus the undercrossing times some sign. Okay, and they go through. In Batson and Seed's original paper, they gave sort of some overly convoluted way of describing how these sign assignment works. But the right way of thinking about it, which I'm trying to, sort of describe in our paper, is something like this. If I don't know how well this, how well annotating in Acrobat works here. A little low tech. Well, okay. Yeah. Delete the comment. Sure. Okay. The rule is you take a checkerboard coloring of the link. Okay, you take the checkerboard coloring, and then at any given crossing, you have to just ask whether the if you put the overstrand and understrand in the right way, how does that compare with the checkerboard coloring? It's the same issues that come up in all kinds of places in knot theory. The sort of type of a crossing. And so that's basically what just governs whether it's over the weight of the overstrand minus the weight of the understrand or vice versa. But that's what's going on here. So you'll see later on there are some shadings coming in. But that's the rule. And then if you check, you can actually look at this. Nice little exercise if you want to just stare at this complexes to verify that d squared is equal to 0. Okay. Now, seeing that d squared is equal to 0 actually now becomes a little interesting. What happens? Let's just go through it, right? If I start, let's just see it this, 1 tensor 1 going this way and then coming back that way, I get an a minus b. Minus times a minus is an a. I get an a minus b times this generator. But that actually then cancels against this way, and that's giving me a b minus a, and so they add up to 0. And right, so they've set up the signs in such a way that it's nice and careful. Okay. Great. Now that's the Batson seed deformation. Okay. Now why did they do this? I'll tell you a couple. I'll tell you the things that they proved. Okay. So number one, this is all invariant. Okay. So if you do Reidemeister moves, the homology of this modified version of Khovanov homology is an invariant, and in fact, it's invariant in the filtered sense, which means that you have a whole spectral sequence from Khovanov to Batson seed. Okay, from like ordinary Khovanov to like Batson seed modifying version. Okay, now if I give it to you with a split diagram, okay, then there are no crossings between components of different weights, right? So according to the rule that we described here, anytime I'm looking at a self-crossing of a given component, the difference of weights becomes 0. So that component piece of the backward differential just becomes 0. Okay. Now, why is it beautiful? What this tells you is let me tell you the last bit of this. Okay. If you have a crossing and the difference of weights is invertible, okay, then there's an isomorphism between what happens with the original complex and what happens if you change the crossing. Okay, that's the third piece of this. And let's just see that in the picture again. Basically, if you imagine that A minus B in this description was an invertible element of my ring, okay, then in some sense up to scaling elements and maybe moving stuff around, sort of reordering the cube, I could just as well think about this as being the complex associated to the reverse differential. See, when you have a crossing, okay, I'm getting basically both possible senses of the crossing. The data of both senses of the crossing is built into the complex in the same way, right? I could think about this, the crossing here, as giving me like maps in this direction, right, which correspond to, you know, a merge from here to here and a split from here to here, and that's what you get from this, you know, positive crossing up here. But if I had taken it the other way with a negative crossing over here, well, I'd be thinking about it as a split from here to here and a merge from here to here. Sorry, maybe that's if I change the lower crossing here, right? Ultimately, it's the same chain complex. Now, the gradings get screwed up under this isomorphism, okay? But the complex doesn't, okay? So what follows from all of this is that actually the assuming that let's assume that all of the differences of weights were invertible, then what you're really just seeing is that this Batson seed homology is just the tensor product of the Khovanov homologies of the individual components. Okay, I guess we can say that if let's try this again. That Khovanov homology Batson seed of L with W is isomorphic to the tensor product of the Khovanov homologies, you know, I guess tensor product over R of the LJs. Okay, and in particular, what we're deducing is that you're seeing now a spectral sequence from the Khovanov homology of the link to the product of homology, the product of the Khovanov homologies of its individual components. And that can be used. Well, the reason that they were interested in this is to get some kind of abstraction of like how many crossing changes does it take to pull a link apart. Okay, that was why they were interested in that stuff. Okay, great. Okay, now what we do what I'm trying to do in our paper is we set up an entire story of functoriality for the Batson seed version of Khovanov homology. Okay, chain maps associated to cobordisms yeah. Okay, now I guess we have to. So what do I mean by weighted cobordisms? A weighted cobordism just means a cobordism in which I've chosen an element of my ring for each component of the cobordism. Okay, and when I do that, I'm going to get a induced map between the Khovanov homologies, the Batson seed complexes of the corresponding links. Okay, weighted links, and of course, and the weights are just induced. So that is, say, if the weight of a given component of the cobordism was some element of the ring, then the intersection of that with every time slice is also going to be that weight. Okay, and every component of every component that abuts that component of the surface is going to be assigned that. Okay, so that's the way this is set up. Okay, and what do you have to do? You just have to write down the Khovanov chain maps in the usual way. Okay, that should be the idea, and you got to make sure that they sort of play nicely with these ideas. But we actually proved more. We tried to prove. Let me say it this way: you have to take the original Khovanov chain maps, okay, and then maybe you have to tweak them a little bit, okay. So the tweaking, the thing that's a little tricky is that actually for many of them, for Reidemeister 1, Reidemeister 2, both Death and Saddles, the maps are literally identically the same. It's Reidemeister 3 where everything gets a little messy. You take the original maps that Barnathan wrote down in his paper, and then you just have to tweak the Barnathan maps and throw in some sort of Batson seed terms into the Barnathan maps. Okay, and if you do that correctly, what you can set this up is so that you see that the associated graded maps with respect to this filtration are the original cobordism maps, right? So that is just like we take the differential and we perturb it in a filtered fashion, we take the cobordism maps and we perturb them in a filtered fashion. Okay, now here's the interesting bit of it. Oh, there, hand.
Can I ask a question?
Yeah, sure.
So you only allow cobordisms between sort of equally weighted components? Like I couldn't saddle two different components together.
That's right. You can't saddle things that have two different weights.
Okay.
Right. Or in other words, if you have specified the weights on the cobordism, then that tells you what the induced weights have to be for every component.
Right on. Okay, thank you.
That's right. That's right. You need that in order to get it to commute, right? In order for the everything to get the F equals FT. Okay. All right. Now here's the cool thing. Under the right circumstances, and it's I haven't quite spelled this out fully, but you have these notions of these crossing change maps, and you have these notions of cobordism maps. Okay, right. So the crossing changes come from if you reverse the sign of a crossing, or reverse the crossing, then you get a specified isomorphism between the complexes. Okay, and the assertion is that that under the right hypotheses, if you spell this out correctly, the cobordism maps actually commute with the crossing change maps. And what I really mean to say is that let's imagine, for instance, I had a cobordism, okay, in two pieces, okay, and I represent it as a movie, right? And the first link has a red and a blue piece, and the second link has a red and a blue piece, okay. And let's say I were to then, take that whole movie, okay, and then pull it all apart. So that is to say, to take every crossing and make red go over blue at every crossing at every stage of the movie. Okay, that's the sense in which this works, right? So there's it's not just and maybe more. You can perhaps try to do a more localized version of this, where you're really interested in like how an individual crossing change interacts with us for a specific movie. This is a sort of more global way of making a statement here. Okay, now let me use this to try to prove our big theorem. Okay, I'm going to do this in like one paragraph. Here we go. Okay, let's see B. Okay, there's bad proofreading on my part. Let's see the component cobordism cobordism between split links. Okay, and suppose that I take the cobordism, just as I was saying before, in which I yank it all apart. You remember my picture from early on, where I basically took the cobordism and I just split it off. Okay, and now the assertion is I can think about C and C prime. C prime is a split up version of this. Okay, as different cobordisms between the same pair of links. Okay. But because I was starting with the same pair of links, these were split links. Okay, and let's say they were really like diagrammatically split links. I had done this with a split diagram. Okay, there were no crossing changes at the beginning and end of the story. Okay, there were just these two cobordisms between the same link. Okay, and the assertion, so the crossing change, the thing that's being commuted with, is in this case actually the identity. Okay, and so the assertion is that these Batson seed, the maps on Batson seed complexes that are being induced are actually chain homotopic. Okay, that's what's telling me when I say that this composition commutes. I'm actually getting the same map. Okay, that pulling the components apart induces somehow the same map on these Batson seed complexes under those identifications. Okay, and now but of course, since the Batson seed differential is the Khovanov differential, it follows with a little bit of careful homological algebra. Remember, morphisms of spectral sequences are really a pain sometimes. So you shouldn't talk about spectral sequences. Talk about filtered chain complexes. But if you do this right, you can actually deduce that the maps on Khovanov homology agree when I yank these things apart. Okay, because somehow the idea is that, right, for split links, Batson's theory of homology is the same as Khovanov homology, right? There's no difference because there's no perturbation. Okay, and the because Batson's theory is Khovanov, you can basically deduce that the maps are really the same. Okay, and that was the result that we needed in order to deduce this. So, okay, let me get a little bit more technical here. That was sort of the big picture overview here. And let's, this has come up in a number of talks. We set this up actually in a broader context, which is this Barnaton tangles and cobordisms description of Khovanov homology, which Onkar was an undergraduate writing his senior thesis with me, and he just, you know, he'd been doing, I think during his junior year, he had been sort of reading, you know, Introduction to Knot Theory, and I got him reading some, you know, the basic introductory to Khovanov homology papers, and then, you know, Barnaton's second paper in that series, where he introduces tangles and cobordisms paper. I hadn't started to read that because I knew he'd like category theory, and he's like, this is the most beautiful piece of math I've ever seen. So, which I had the same thought when I was, you know, starting out as a graduate student, first reading this this result. So that was what got us really sort of talking about this subject. So Barnaton sets up this amazing way of thinking about Khovanov homology in this sort of abstract category. Okay, and what is the and this, it becomes this way in which you can talk about the Khovanov complex associated to a tangle. Okay, now you take this category. So if I choose an even number of marked points in the boundary of a disk, and I think about a tangle with boundary those points, okay, there's this category that you can write down associated to this. And what are the objects of the category? The objects are these planar tangles that live in the disk. They're just sort of crossingless, you know, one-dimensional submanifolds, properly embedded submanifolds with boundary of this the disk. And morphisms are cobordisms in 3 space between those things. And what Barnaton shows us is that the right way to think of Khovanov homology is that you can really think about the complex associated to a tangle as being some kind of formal chain complex of objects in this cob3 mod H cob3 mod L. I can never remember what it is. Like L is for local relations. If you don't know what that is, don't worry. Okay, so now we wanted to say, and one of the things that's great about Barnaton's discussion here is that it enables you to really make these stories local. Okay, so for instance, if you want to prove the Reiner-Meister invariance, okay, you basically just need to show that the complex associated to this Reiner-Meister 2 tangle, right, this one, a Reiner-Meister 2 thing, you just need to show that the Khovanov complex of that is isomorphic to the Khovanov complex of that. Okay, so that's the idea that you want to try to show. And once you do that, you can basically then just sort of tensor, quote unquote, with all the rest of the crossings and get that. It gives you this really legitimate way of thinking about the Khovanov complex as some kind of funky planar algebra tensor product of local bits. Okay, and so once you know that the invariance at this local level, then the invariance at the global level just immediately follows from that idea. Okay, now we'll say in a similar fashion, what Barnaton was able to do in that paper is that if you want to, for instance, prove the movie move invariance, you just need to make some statement about how the local moves, the local maps on movies behave with respect to those cobordisms, right? And prove it at a local level, and then just tensor those over the rest of the complex. Okay. So what we set out to do was to do all of that for the Barnapon perturbation, right? And I really so for the Batson seed perturbation, and really build the entire Batson seed story in the more abstract setting of this Barnapon tangles and cobordism story. Okay, now the thing that's funny about it is that it no longer satisfies d squared equals 0, but it becomes some kind of curved complex, or I don't know if matrix factor. I don't think matrix factorization is exactly the right word. We were calling it a curved chain complex. I'll just give you a picture of this, right? Like it's the basic thing that you can imagine. Okay, so let's imagine I give you a crossing. It's the simplest tangle you can imagine, a one crossing tangle. Okay. You should understand that complex as being basically the two possible resolutions. Here's the 0 grading, here's the 0 resolution, here's the 1 resolution. Okay, now in one direction, the morphism is just the saddle cobordism that goes one way. Okay, and in the other direction, the morphism, the bit of the differential is the saddle cobordism that goes the other way. Okay, now you might say, well, what's d squared? Well, d squared is supposed to be, if I go this direction and that direction, it's just supposed to be the composition. So that's two saddle cobordisms. That's giving you a torus, right? That's giving you a genus 1 thing, a genus 1 cobordism. Let's see. Here we go. Oh, well, sorry, it's not exactly genus 1. I didn't mean that. What I meant to say is it's giving me a tube. That's what that looks like, right? It's like two vertical curtains and a neck between them. Okay, but then you can use the neck cutting relations, which have been alluded to earlier in this conference as well, which is to say that this is now just the same thing as just sort of, it won't let me draw a dot. There's my dot. I'm sorry, I was planning to do this as a chalk talk, and then circumstances interfered, and I had to do this from home. So I had slides that I had to was able to adapt. But yeah, so you get like a very nicely controlled d squared. It's not that d squared isn't 0, but you can figure out exactly what d squared is. Okay, and one of the things that we're able to verify, for instance, is that in Batson seeds, d squared equals 0 proof. It comes from you can think about that as coming from like some local contributions that all add up to 0. Okay, which so we really sort of tried to build up the algebra of what should twisted complexes or / matrix factorizations look like in this setting of Barnaton's tangle and cobordism formal complexes. Okay. Great. In a similar fashion, you can set up the crossing change isomorphisms completely locally. Okay, and I've just given it to you, right? So the top thing is representing this is from our paper. The top thing is giving you the complex associated to one of the crossings, and the bottom thing is giving you the crossing is the complex associated to the other crossing. And I've just given you the chain maps that go back and forth between them. And seeing that these are isomorphisms, I guess you can write down the chain maps in one direction, but in order to get it to get them to be isomorphisms, you need to I guess what you observe is that the composition of both ways is b minus a times the identity, and b minus a times the identity. If b minus a is a unit, that's an isomorphism of complexes. Okay, and so if you want to understand, how do you see how the crossing change isomorphisms interact with the movie moves? Well, a crossing change that's disjoint from a movie move, that's far away from a movie move, everything has been so localized that now it's guaranteed to me. Okay, and I really think that that this might be useful in other settings. Something I've been wanting to learn a little bit more about is what the sort of whole scan lasagna algebra business, which I really haven't spent any time with, and I would love to know if there's any, if this being able to pull surfaces apart is ever useful for anything else other than than just this. So that's what I kind of want to advertise. All right. So any questions about this? I want to say just a few more. I'll say a few words about the ribbon concordance application because it's kind of cool. But okay, great. Okay, so what's a ribbon concordance? A ribbon concordance is well, you know what a concordance is. A ribbon concordance is a concordance is called a ribbon concordance if, when you think about the projection to the time coordinate, it's a Morse function with only index 0 and index 1 critical points. Okay, now which way is from and which way is to is a little bit completely screwed up in the literature. Cameron Gordon defined it one way. Ian Zemke then sort of influenced in his recent papers about the sort of changed what from and to mean, in which way is.
So we do lost two positions. So
I can't hear. So, was someone trying to ask something? Oh, no. Okay. Okay. Yes. Right. Okay. So ribbon concordance is a concordance. So if you play the movie, you only see births and saddles and no deaths. Okay. That's the directionality that I think about it is. Okay. We say that a given link is ribbon concordant to another link if it's possible to do this, and the symbol that is used is a sort of funky less than or equal to symbol. Okay. Now, here's a picture. Here's like what a ribbon concordance looks like schematically. Here's what not a ribbon concordance looks like schematically. Okay. Now it was. This is a transitive relation and a reflexive relation, of course. But it's not. It's clearly not a symmetric relation, or it's not a priori. Well, it's probably not a symmetric relation. And the question that Cameron Gordon asked was whether it's truly an order relation. Okay, so it's an order relation. What does that mean? His conjecture was to say that if you have two knots, he would say that this is a knot setting, but maybe you make the same conjecture, but I'm not sure. That if you have two knots and one is ribbon concordant to the other, and the other is ribbon concordant to the one, then they must in fact be the same knot. Okay, which is what you would need to have a partial order. And this was a conjecture that sat around for quite some time until sort of interest was revived in it a few years ago by Ian Zemke. And then out of the blue, earlier this year, Ian Agel came along and proved the whole conjecture. This lovely 6-page paper. And as I was mentioning before, there's a story in Quantum magazine about Agel's discovery, which I'm not sure, I mean, for this audience, it will make sense. I'm not sure it actually explains it to like a general audience reading that article would get any more out of it. But the general philosophy is that if you have a ribbon concordance from L0 to L1, then one link is simpler than the other link. The first one is sort of simpler, and that lots of invariants should be able to measure that. So that is to say that the values of invariance of L0 should be quote unquote smaller than the values of the invariance of L1. And this, I was trying to think about this, whether this actually follows from Agel's work. Doesn't necessarily. But what one of the things that does say is that as evidence for the conjecture before it was proven, having those kinds of results give you some indication that if you have two mutually ribbon concordant links, then their invariance should be the same. If there's invariance for like, numbers or groups or something nice and small, you should be able to say that the invariants of L0 are sort of no bigger, equal to the invariance of L1. That's the sort of philosophy. Okay. Now, I'll mention here what a version of this that we were interested in. There are two sort of weakenings of this notion. One is a strongly homotopy-ribbon concordance, which is a sort of terrible name, but being strongly homotopy-ribbon is it's a condition on the complement of the cobordism. Okay, the condition on the complement is that you can build it. You can build the complement of the cobordism from the first link, by the complement of the first link by using only 4-dimensional 1 and 2 handles. Okay, so it is a relative handle of the structure that satisfies certain properties. Okay, the way to think about that is that that you get a handle structure for the complement whose critical points or whose handles correspond to the critical points of the Morse function on the surface itself. Goffman's book, if you has a whole discussion of this with comparison to filling a bathtub or something, which is useful in some ways or not. And then it's called homotopy-ribbon if you get an injection on pi1 in one direction and a surjection on pi1. Oh, I left out my pi1s here. Pi1 of this and pi1. Okay. So that's what it should mean, what a homotopy-ribbon concordance ought to mean. And it's unknown. So it's unknown whether the these implications, the converses to these implications hold. So clearly, if two knots are ribbon concordant and they're strongly homotopy-ribbon concordant, and therefore they're homotopy-ribbon concordant, it's unknown how you would distinguish those things. Okay, I believe Hegel's proof only lives at the ribbon concordance level. I'm not positive. I don't think it can be extended, or I don't think it. I think he mentions that case, but okay. So the theorem that I'll mention, and I'm almost out of time, so I'm not going to really say much about this, is that so Zemke and I proved that if you have a ribbon concordance from L0 to L1, then it induces an injection on Khovanov homology. Okay, and in fact, the Khovanov homology is injecting into the Khovanov homology of L1 as a summand. Okay, and one of the things that happens in the proof is that you take the cobordism map. The cobordism, you take its reverse map, the map induced by the reverse cobordism, and then you sort of study that thing topologically, and you're going to try to pull off some spheres. And in the ribbon concordance setting, you end up being able to sort of tube off, separate some spheres by tubes, and those spheres are like unknotted spheres that live disjointly from the rest of the cobordism. They're actually like locally knotted spheres, and that's how the proof works. Okay, so then you try to replicate the same proof in the strongly homotopy-ribbon setting. And what's you almost can do it, but the problem is that the spheres that you needed were no longer unlinked. You get these spheres, but they're no longer unlinked. And so that was what had initially gotten Onkar and I thinking on the subject of thinking about can we do unlinked spheres in the complement of a cobordism change the map, or do they kill it? For spheres, they should kill the map. You should know that everything's 0, and that was exactly the result that we needed from before. Okay, and so it's this splitting result that was what enabled us to prove that. So I think that's a good place to stop. Thanks for listening.
Yeah, any questions?
Yeah, sorry, just remind me because I got confused. So ribbon concordance, every ribbon concordance is strongly homotopy-ribbon?
Yes.
Okay. Yes. Okay.
Yes. Right. So the point is that if you want to write down a handle structure for the complement, the one handles of the complement correspond to births. The two handles of the complement correspond to cells, and the three handles still correspond to deaths. So if you have no deaths, you have no three handles. And then it's a result of that condition, using work of Gersten, Haber, and Rothaus, which is known to Gordon, is actually enough to tell you that you can believe the strongly, which is to say that you get an injection on pi1. Well, one way that the surjection on pi1 is one of the three handles that tells you that if you turn the cobordism around, you have no one handles, and so you get a surjection on pi1. If for the other direction, you need a little bit of group theory to actually produce this. Yeah. But what's surprising here, I don't know if we'll see this, is that like most things that we know about Khovanov homology are sort of diagrammatic in nature somehow, right? Like we know things about they're not, or they're generally not complement based. They're not about the complements of links. Right? We would love to know more about the relationship between the Khovanov homology and a link and its complement. To more traditional topological notions about its complement. Here's the theorem about maps on Khovanov homology that is not based on really on the diagrammatics of the link. It's based on knowing something about the complement, even if that complement is not, even if that handle structure on the complement is not like directly connected to the diagrammatics of the cobordism, we're managing to do something about Khovanov homology from that. So that was, I think, kind of surprising to us.
I have a really basic topology question.
Sure.
I probably should know the answer. What's the simplest example of linking between two spheres?
Simplest example of linking between two spheres. Let's see. You could just do. I mean, you could do just some kind of movie, and get. You just have to get them to tangle up a little bit. I don't know how you'd measure the linking, but or how you measure simplest. But do
movie, I could probably draw a picture.
Huh? I mean, for instance, right? Like do a movie in which sort of one of the unknots passes through. Start with two unknots, have one of them pass through the other one. I don't know if that would actually produce a non-trivial link. That's probably too simple to produce something non-trivial. But
maybe if I could continue something. One way of doing this is to take a tangle that has two components, put the four ends of the tangle on an axis, and then spin it around the axis inside floor space. And so it's like we've seen the construction of twists from two knots. And you can do this with tangles and you
But you need to twist. You're saying you need to twist?
no, you don't need to twist. You could just spin the tangle.
I was trying to draw a picture. I thought that if you just spun it from my face.
yeah, you could do a tangle, or you could do a spun.
Okay, thanks.
I have a question. So you're saying that the functoriality maps commute with this like crossing change morphism?
Yeah.
But so I was trying to understand what that means. So so the crossing change morphism, I understand that the components may have different weights, but the crossing change morphism is some like genus one cobordism from one thing to the other, right?
Well,
so I mean, right?
yeah, I mean that's an interesting, right? So but I don't think that the crossing change map is not the cobordism map induced by the.
I guess I know I understand that. Sorry, but could I somehow consider this like cobordism category, like a weighted cobordism category, and kind of formally join this crossing change map as some sort of genus one type of picture relating to different weight. I don't know. Is there some like cobordism way of viewing this crossing change map? And I don't know.
Huh.
Is there any benefit to doing this? I don't know.
I mean, I think there's really. I would think what I would like to say is that actually it should be corresponding not to a an embedded cobordism, but it should be corresponding to a the movie of a strand passing through another strand, which is that it's like two surfaces intersecting at a point.
Oh, okay.
And so I think, yeah, I think we didn't have a clear enough understanding of the movie, of like how to think of movie moves. We didn't prove a complete like description of like everything's invariant under all sort of homotopy. The way we did it was to say, you can consider a cobordism and you can consider the like completely split version of the cobordism, where you just separate everything all at once, which you can sort of localize it. Like you imagine, for instance, a Reidemeister 3 move, and then the corresponding Reidemeister 3 move where you like reorder the components. That Reidemeister 3 move corresponds with the composition of code. That Reidemeister 3 map commutes with the crossing change maps needed to reverse, to permute the heights of the 3 components of the Reidemeister 3.
Right.
So yeah, I think you probably could turn this into some kind of local movie move story about like homotopy of diagrams maybe, and like or some sort of story about surfaces with self-intersections, and allowing some new movie moves that allow you to do some kind of finger move that introduces to self-intersections and remove it. And I actually think that would be great to know how to do when you're doing it between distinct components. But I don't think we had a clear enough statement of the topology there without having like fully gone through Carter and Saito's books, etc., about exactly what the right statement would be.
More questions? Okay, if this is not the case, yeah, let's thank Adam again.
Thanks for listening.
Oh, no way, really? Thank you.
If you post this, it could be a